So what do we do with smart cities? Basically, we are talking about smart traffic management with 3 pieces of software. The first one is called PTV Optima, which is the real-time planning and modeling software for controlling traffic using predictive analysis, not only what is happening now on roads, but what may happen into the future. This particular software has found its way mainly with many police authorities in the world, because around the world, it is police who has the responsibility for traffic management and operations. And then we talk about 2 absolutely amazing pieces of software for Indian conditions, which is Balance and Epics, which is actually used for traffic signal control. And we will explain some of the trial works which we have been doing in India with it. So Optima is the solution for dynamic traffic signal control using real-time data fusion and prediction. Let us see what we are really talking about. We are talking about firstly getting data from multiple sources, which is big data. We are fusing this data in real time on a GIS platform, but because there's a transport model behind it, you can then compare scenarios in real time. So just like you have transport model to test impact of a breakdown or a new highway or a new cinema or a new say shopping plaza, you can create scenarios. So if suppose you have a VIP movement through the city, let's imagine now maybe President Trump, it looks like maybe Trump, if you're following news, if he's coming to India, it will be a big challenge from security forces to arrange all the movements around. And the police want to make sure that everybody is going to be safe around it. So if that is going to happen, then how do you make sure that you can really be proactive with your traffic around? Because what you really don't want is a security havoc or a congestion havoc when VIPs move around. This is the big challenge in some of our cities. So the idea is to create scenarios, to have an action management plan, and Optima acts as a hub for information, not only testing, but information control as well. It becomes a method for evacuating your cities in case there is a problem or an emergency or a disaster, and it's all based on sound traffic modeling techniques. So how many of you are using Google right now for navigation? Okay, almost all of you. How many of you got no smartphone with you? No smartphone? Nobody. More than one smartphone? More than one? Quite a few. Okay. So this is what it is. This is the smartest device which you have, all of you. It's got more power than 10 IBM 486 or Pentium computers combined together. So this is the smartest processor you got now. And in time to come, we really don't know what we may have in terms of technology. So what Optima does is, firstly, it takes data from various sources, combines it together, and then gives you a good harmony of what's happening. So we take data from various in-car navigation systems, GPS devices, data from navigation companies such as TomTom, Here, and Inrix, and we combine it together so as to understand the current status of both private and public transport vehicles 24/7. This is live data. We also take information from emergency broadcast control rooms. Suppose somebody has an accident, they report it to the radio, say that there is accident, say on ABC Road. We get information from there as well. We actually, as a part of Optima, create a short-term model. This model is created in vSoom because that becomes a hub of scenario testing. We take information from any type of CCTV camera, ANPR camera, loop detectors, which may be present on ground by creating an interface into existing or proposed systems. One of the most important information sources is the VMS sign. If you do not have VMS signs, the biggest VMS which you have got, or a variable message sign, is your mobile phone. We create interfaces into that for understanding what's happening on ground. You can control traffic in an urban environment through traffic signals. So having an adaptive traffic signal control system is one of the important parameters to have a good traffic management solution. And this can be embedded inside the program if it is not present in the city, or if something is already present in London, for example, there is Scoot. In Australia, there is CATS. In other cities, there are other systems such as Balance and Epics. We can create an interface from these existing systems into our system, as long as they have a communication switch. And I'll talk how that is done as well. As a part of Optima solution, you create an app or you open your APIs into existing city management or planning apps. So in Abu Dhabi, for example, they have their own app which is called Darb. In Qatar, there is a bid out. In Pune Smart City, you will have an app. We will create either a full app or an API for journey planning and infomobility into that app, so it allows people to see what is happening on ground. Most of the people are either using Android or iOS type of phones, and we have teamed up with data companies which have got access to iOS and Uber data, which gives us information of what's happening on ground. Of course, these companies charge you for this data to understand what's happening. We also take information from Bluetooth devices. I will talk about our controller, which we have built for Indian environment, and the controller comes up with a Bluetooth data recorder. So just check on your mobile, how many of you have got Wi-Fi or Bluetooth signal on, receivers on? Can you just check and raise your hands if your Bluetooth or Wi-Fi is on right now? So that means you're leaving your Mac ID. If I put a detector over here and I put a detector into, say, the exhibition hall, I will know exactly when you have moved from here to there. Not you, but a phone has gone, because the data is anonymized. And we take information from all emergency vehicles as well, such as police, fire, and ambulance, because they take this information. So what we do with it, once we get all this information, we get complete overview of our roads and public transport 24/7, 365 days a year, much more than Google. But what Google will not give you is what will happen in half an hour from now or 2 hours from now when you have a flight to catch. We can predict that future as well, and we can do it very accurately for the next few hours or a few days. So it's like a weather model, okay, in which the accuracy is very high, closer. And because there's a model, you get real-time KPIs. One of the big problems in Indian cities is perhaps, for example, pollution. And if I want to know what is happening with the pollution or what's going to happen tomorrow, okay, I can predict that very easily as far as transportation systems are concerned. And these are continued, or they're always collected in real time, so you can calibrate your model in real time. Those of you who have a problem to create strategic models, this is a source of very good information. And then let's take, for example, you have this VIP movement through the corridor. You can then test strategies at what will happen or what should I do if this happens. So I maybe need to change traffic signals, I maybe need to change VMS signs, I maybe need to tell people, please don't use this route from 11 o'clock to 12 o'clock in the day, because we are expecting some significant delays around. So you can just press a button and you can change that. All of this forms a part of big data. Inside it comes a journey planner as Hyperpath, which is embedded to the API of the city app for journey planning, which is fully multimodal. So what we had before was software, data, and network, which goes into a dynamic model. All your hardware outside, which is online, that leads to data fusion, and then you can test your strategies in real time and give short-term forecasts. Your operators enter some events into it, you run the models, and then you get some results of what the future strategies can be. So say strategy number 3 is best. You press one button, and then you can override your traffic signals. You can publish new messages in your vehicles, new route guidance, and new VMS signs. And that is really what is happening. So you're going from a state where you get, this is London, for example, partial data from vehicles. That is only from traffic signals. Here I'm combining the data with GPS data from various vehicles. And then I'm predicting usual conditions. But my objective is not just predicting usual conditions, because if I just put congestion sign, which is on this main road, everybody will still use the main road. My idea is that I utilize a whole network. And to be able to do that, I must change some strategies. That is, maybe make a diversion route better, which can be done by changing traffic signals, publishing a new VMS sign, and maybe even giving messages to people that please use this bypass route, which is much better. So then, of course, when you publish this, you will have some people who will still use the main route, others will use a diversion, and they both arrive in real time. And that is what you achieve with Optima. So here, again, the example, you can test your strategies, which can be a combination of various changes and so on and so forth. And you press one button, and within 2 or 3 minutes, we are talking for the whole city of London, perhaps, the computation to be done. So you can imagine, I don't know how much is the current transport models taking to run, but this is massive, massive computation time, which is very, very quick, because it's done in real time. So within 2 minutes, I can test scenarios. Scenario number maybe 1 is the best, and I press a button, and you override everything. For people who are interested, I can actually show you the interface from example, from sites from Turkey, where we have developed the interface, and you can actually, I can control traffic signals from my mobile phone if I need to make them fast. So this is where transport modeling sits together into the world of ITS and comes into real-time management. So looking at this particular approach, this is where Google is, that you can only do observed data, and you cannot forecast, and of course you cannot have any decision support tool. But with this tool, you can achieve all of them. How do we really make sure that this is where it's already done. So various places, Paris, Dubai, London, Munich, Vienna, Russian highways, Moscow, Abu Dhabi. It's new technology. One of the biggest contracts which we won recently was Enterprise Command Control Center for Dubai Police and RTA. And this is huge, which is going in. It's a $150 million project, which is really making the city much smart. So very, very quickly going, I want to talk about the two components of traffic signals, which is area traffic control and how that is achieved, and how that can work very well for Indian conditions at a very low cost. We've got two systems over here. One is called EPIX. EPIX is our vehicle actuated control software. It is only software. PTV is a software company. We are not a hardware company. And EPIX does local optimization, which is individual junctions, and it looks at full traffic signal priority done every second. And then the parent software by which EPIX communicates is Balance. Balance is an area traffic signal control software. Both of these have got links inside Vism, so you can see how it will work. And EPIX coordinates the signals, produces plans, and optimizes the entire area every 5 minutes. So what happens is that you measure something. Inside the software, you have got evaluation and optimization algorithm. There's a traffic model, impact model, control model, and you generate signal plans, and then you act. And the evaluation is done on true optimization techniques. What happens inside EPIX is that you have some detectors which will detect what is happening on ground, and they are essentially checking queue lengths, saturation flows, cyclic profile, public transport information, and the push button data, and it can also predict to what will happen for the next 1 or 2 minutes, for a few seconds. When we look at the vehicles, we are looking at the time when the public transport vehicle or a vehicle will enter, the check-in point, and then the checkout point. So we are making biology. What happens is that we have two solutions, a father and the mother. And the father and the mother come together and they have a baby. The baby has got characteristics of both the father and the mother and some random characteristics. Now if this baby solution is good, he is retained. If he's bad, he's deleted. So that means that in the peak hour, where I would have had with a normal conventional optimization technique only fixed answers, I can have many, many answers over here. And over some time, my solution is becoming more and more intelligent. So it's like a smart traffic cop who is utilizing his mind to become more intelligent. Here I'm using heuristics for optimization, which is really the state of art right now. And this is mathematically much more sound for Indian condition, where we really do not know how the optimization may work on ground. Then this is one of the key things over here. And then we are optimizing our plans and coordination every 5 minutes. And the local adaptation is done by EPIX. So you can see that inside various times of delay over here, you can have various solutions. And many possibilities are possible to reduce the answer rather than one fixed one. So this leads us, why this whole system of EPIX and Balance sitting with Optima together is better. Because it is looking at actuated and predictive control. So nothing actually works right now with predictive control. The origin destination matrix is done via Bluetooth. This is how the control box really looks. You have got some cameras which are looking at, this could be loop detectors, not just camera, which look at what's happening on ground. The brain of the camera lies inside the algorithm of image detection, which is very, very accurate and calibrated for Indian conditions. This communicates via Wi-Fi to the control box where the algorithm sits. The control box has got various ports over here, a Bluetooth detector, a local memory of about 250 megabytes. So in case the link is broken, it can act locally. It can be connected via fiber optic or 3G card to the central control room where Optima and Balance are sitting, and they can override the command. And it has got interfaces so as to communicate to a local existing signal controller. And that really allows this existing infrastructure to be communicated with our stuff. You can look at emissions, you can have multiple objectives. So you may have one objective, minimize pedestrian delay. Another objective, minimize bus delay. Another objective, maximize car throughput. This is all possible. You can work with any detection system. And because you're using cameras, you can work on non-lane based traffic, slow-moving traffic. I've explained they're not deterministic equations. Using evolutionary algorithm, local adaptation is possible. Safety solutions are integrated. And most important thing is that you can work with any signal manufacturer. Doesn't need to be Mr. A, B, or C, and it's low cost. So that's how the junction is set up. Cameras looking on each side, communicating to the controller. The controller is then talking to the unit via Wi-Fi. The unit then talks to the old controller, and over internet it goes back into the server where Optima and Balance are sitting and communicating together. So that's the camera technology which is using one fisheye camera and 4 fisheye camera is dual sense, using one for surveillance where the police can have access, up to 20 users can have access simultaneously. It's digital pan tilt zoom and calibrated for junction turning counts, plus 4 cameras calculating approach counts. This is how some of the existing videos look. Here I've looked at condition from Delhi where I'm counting the number of vehicles, just one straight line, and motorcycles, 3-wheelers, everybody being counted. This is from examples of elsewhere. We're getting fisheye camera with turning movements, and doesn't need to be lane-based traffic. And in fact, in the night time, the detection is even higher because we're looking at the headlights. And this is all possible. That's how the box looks. So that's integrated with an old controller. This is a Siemens Maestro controller working inside. And you can see the GPS antennas and also the Wi-Fi and the Bluetooth detection antennas. I've explained you this box, the way the box is created. So it's pretty simple. These are existing signal controllers. That is a CDAC controller, which is working on a device. And that's typical Indian condition. You don't need to change all of this. As long as you get a communication port via RS-232 or Ethernet, our box can be integrated onto the top. So, which is really, really low cost. These are the existing controllers which are present anywhere. That's an old controller which is being used by Keltron. It's a Motorola controller. Even they don't know the interface for it. So as long as we have an interface, we can communicate. What do you mean by interface? Just like your mobile phone has got a charging port, that is an interface, because it's not just a charging port, it's also a communication device to copy data in and out. So we just need these commands. You open the interface to the controller, we can override it. Look at the condition of this controller. This is really old stuff, but that's what is used in India. The wiring is everywhere. If it was in Europe, it will not go anywhere. Same is with some of the, if the controller is useless, we can change this. This only costs $500. Here it's the UTMC unit supplied by Siemens. This is in Dubai, and you can see over here the interfaces are very neat and clean, and the integration can be achieved. And then you can have a control center. You can have a simple control center like this, or more complicated, or even on your mobile phone that is separate. I will give it to Prabhu. Prabhu, you got 5 minutes just to show both the case studies. Okay, you want to show very quickly?
It's already 15 minutes late, so I'll just skip many slides. So basically we did a case study in Delhi and in a Pune. So this is a case study in Delhi which we took at Lodi Road, and so these are the normal traffic studies which we carried, and these are the few results of this, and the validation part, and we did with the GH values, and this is the result for GH values for Delhi, and again the travel time validation part, and the simulated on the average observed travel time, and these are the few snapshots from the model itself. And the main thing is, this is the chart which is the travel time, the queue length. You have the reduction in the travel time, queue length, and the speed has been increased once you integrate the balance and epics on top of the base model itself. And this is again the travel time comparison between the observed model, the simulated model, and the balance model. So I'm just skipping, I'm not explaining anything. So these are the different charts from the average speeds.
The average delay has reduced dramatically compared to what is there at present all across, on almost all the junctions. So 45% reduction of delay is just significant in what we can achieve by this particular technology.
Yeah, and again this the network delay and the average speed and the speed profile from the entire network. And we also have an emission integrated into it, so we can just calculate the emissions. So these are the reduction of emission once we have the the integrated balance and epics model into the simulation model itself.
So you see that, in Delhi, the air quality can be improved by 10 to 15%, which is really significant. And we are talking of this pollution and smog and whatnot in our cities. I think this is a big significant contributor for the time to come.
Okay, the next case study is a Pune. So we took a Karve road as a stretch, which is of 3.2 kilometers. And this is the case study section, and the same data collection has been carried. And these are the volume counts and the coded model, and again GH calibration and the travel time calibration part, and the snapshot from the model itself. And here is the result for the comprehensive one.
This has been done only last
This
night.
is just
So we are
this is just a draft.
simulated result, and even we have not seen this.
Yeah.
The next step for us is to go on ground and to actually change the controllers.
This
We
is just
have the permission. We just need to make sure that we can implement it next week on ground.
because this has been tested only with the cycle time of 90 seconds. We are evaluating with different cycle times for the entire network. So this again has to be tweaked a little bit. So, and again this is the comparison between the observed, simulated and the balance model and the queue length. So I think two gentlemen are from Pune, so they know about the null stop. So it's majorly a big intersection, so we have reduced a significant queue when integrating the balance and the epics on top of it. And again the average journey delay and the speed has been increased and the average network delay has been reduced. And this is the comparison between the Delhi and the Pune with the different KPIs. And
So
this
these
is
are the two videos. This is
this
simulated
is from
stuff.
Delhi.
Yeah, this is from Delhi. I think let's show Pune because even we have not seen. We can show the videos later on to people. All these results will be disseminated. All the presentations will be available to all of you online as well. So let's see how does this look, because this is also new. I have not seen this. We have not seen this ourselves.